Okay. Hello, ladies and gentlemen. Can you see me? And if you can see me clearly, and if you can see the board, can you please just type yes, 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 and just say, I'm going to write something here and make sure that you can see the writing clearly as well. Now, feel free to join the live chat. If you have any questions, you can just put the questions there or give me the comments. If you cannot hear me or if you see the sound is lagging or video is lagging, just let me know. So keep communicating. Say hi to each other here. Good to see all of you here. Okay, so obviously, I cannot print the questions out for you guys, so you need to have a question in front of you. So I hope that you can share the screen a little bit, maybe video on the left-hand side and you got a question on the right-hand side. And I'm gonna do my best I got a small whiteboard here today, so I hope I can fit everything into the board. So my handwriting can be slightly smaller than usual. Okay, now, can we start? All good? Okay, I'm trying to cover 4 questions today, so let's go for it. Now, the first question is quite an interesting question. I like it a lot because I was doing the AIME questions the other day, and I just picked this one from that. So the question says, Z plus 1 over Z is equivalent to 2 cos 3 degrees. And what they're asking is you need to find the least integer that is greater than the given, which is Z to the power of 2000 plus 1 over Z to the power of 2000. All right, is my audio okay? Is it lagging? Because yesterday my year 9s commented, saying my audio is always lagging. So I hope that it's not today. Okay, so let's have a look at the first one here. From the given information, we need to find out what Z is. So if we know what Z is, then this will be much easier because we can use the Moore theorem to get this sorted. Okay, now here, what I have done is I multiply both sides by Z so that I don't have the denominator here. So that will give me Z squared plus 1 equal to 2 cosine 3 degrees Z. So if we observe what we got here is we got a power of 2, power of 1, and a constant. So that is quadratics. Now, the tricky part is we can't really easily factorize this. So I decided to use the quadratic formula. Okay, now when I'm doing the quadratic formula on the board, can you please use the quadratic formula to do it on your own paper as well? So that don't look at me, do your own work, and we're going to match our answers together. Okay. Sorry, kids. Sorry, students. You might hear my sons crying. All right. I hope that you get to this stage now, and then we can actually continuously take the common factors out. In fact, I can see you got 4 and 4 here, so I can actually take the 2 out from here. So I got 2 cosine 3 degrees plus and minus, because this one can be, okay, I'm going to just write it here. So 4 cosine squared, 3 degrees, sorry, not 30 degrees, 3 degrees and take away 1. And then 2, square root of 4 is 2, so I can say it's 2. And then I have cosine squared 3 degrees, take away 1. Okay. Now from here, what I can quickly do is I can cancel the common factor of 2. So 2, 2, and 2, they are all gone. And now it's actually getting simpler. So this is cosine 3 degrees plus and minus. And if you look at on this side, we know the trig identity is sine squared plus cosine squared is always equal to 1. So this actually tells me I can switch it to something. Yeah. So that will give me negative. So that will be cosine 3 degrees plus minus square root of negative sine 3 degree squared. Okay, is everyone okay until this stage? Does everyone understand what we're doing here? All good? Okay, so if we can tidy up a little bit, so this will be this is what we get here. So if you look at it, now we're actually getting a polar form here. So one of the solution that we can use, okay, one of the solution we can use is the positive one, because the positive one is the polar form. So I'm going to say that for now, because I know I've got two solutions, but I'm going to use one of them. So z is equal to cosine 3 degrees plus I sine 3 degrees, which is equivalent to cis 3 degrees. Okay. Now let's actually use this one solution here for the right hand side. What the question is actually asking for. So we have z to the power of 2000. So cis 3 degree whole thing to the power of 2000. We are going to use the De Moivre theorem. So that will give me cis 3 degrees multiplied by 2000. Remember, the modulus is 1, so 1 to the power of 2000 is still 1. And then we have 1 over cis 3 degrees times by 2000 here. Okay. Now, before we do that, actually, just quickly have a look this part. I don't want to go further because the number is getting really big and it doesn't really help me. But 3 degrees times by 2000 will be 6,000 degrees. And think about 6,000 degrees is how many revolutions that's around. So if we keep spinning, it's actually 16 revolutions, 16 full circle, and then it's plus by 240 degrees. So I can rewrite this. This is equivalent to cis of the 16 revolution, okay, 16 revolution, and then each revolution is 360 degrees, and plus 240 degrees. So therefore, it is equivalent to cis 240 degrees. So we don't need to actually write cis 6,000 degrees here. We just need to actually make sure that we know this is actually 240 degrees. Okay, I'm just going to quickly, can I erase the left-hand side? Is it okay? Because what you can do later on is you can go back to the video again and just rewind it, and you can see this part again. All good? So I'm going to erase this part now. Okay, no problem. Thank you, Alison. Okay, so now what I have done is rather working with this, okay, instead of substitute it first, I actually combine them into one fraction because I think that will be easier. So if I combine them into one fraction, so denominator is the same, so z to the power of 2000, and obviously what I have is z to the power of 2000 squared plus 1. Okay, now what I want you to do is, on your own booklet, can you please try to substitute what we got here, which is cis 240, into this expression here, and then you are doing your work and I will do my work. Okay, so don't look at the screen first, just try by yourself, and we're going to match our own Hello, Kusha. How are you? I'm good. I'm in the middle of the lesson. Okay, no worries. Yeah. Okay, talk to you. I'm doing it now at the moment, 10 o'clock. Yeah. No worries. Okay. Okay, bye. Okay, gentlemen. So what I'm trying to do is I substitute into it. So the whole thing squared, that means we actually double the angle. So which is cis 480 degrees plus 1 divided by cis 240 degrees. So I was trying to work out what is cis 480 and what is cis 240 degrees. So on the right hand side, I hope that you can see clearly. So cis 480 is same as 1 revolution plus 120 degrees. And then you can I break it down. So the original format. So I have cosine 120 degrees plus I sine 120 degrees. And then again, 120 degrees is actually equivalent to, you use ASTC, if you look at the location of the angle, it is actually equivalent to negative cosine 60 degrees because it's in the second quadrant. And then sine 120 degrees is actually same as sine 60 degrees because in the second quadrant, the sine is positive. And then I know that from the exact values, cosine 60 is half, which is same as sine 30. So negative half plus I square root 3 over 2. And then I move on to figure out what cis 240 degree is. And that is same as cis negative 120. So that is actually in the third quadrant. And because of that, I know the angle is negative. And I use a reference angle of 60 degrees. So it is equivalent to negative cosine 60 degrees. Take away I sine 60 degrees, and which will give me negative half negative I square root 3 over 2. Sorry about the small writings here. Just don't have enough space on the board today. I cannot draw everything out. So basically here, we use ASTC and use the exact values to determine what are the values of the cosine and the sine. And now I'm going to put them back into the expression here that I got. So which is, I got negative half plus I root 3 over 2 plus 1 over, and the cis 240 is negative half, take away I root 3 over 2. All right, just let's keep tallying up. 1 take away half, so that will become, so I'm going to write on this side so that I have more space. So I have half plus I root 3 over 2. It's actually looking quite good because if you look at the bottom part also got half and the root 3 over 2. Now, if I take negative 1, the common factor, out from the bottom, what I have in the bracket is half plus I root 3 over 2. Now, what you can see is perfectly, I can cancel the common factor on the top and common factor at the bottom. So the final answer will be negative 1. So what we got here is z to the power 2000 plus 1 over z to the power 2000 is equal to negative 1. So we know the answer. Now we are able to find the least or the closest, the least positive integer that is greater than negative 1 will be 0. Okay, so now I can make the conclusion. The least integer greater than this is 0. Okay, so I put this question as a warm-up question is purely because it's actually testing our demand skill and also the ASTC, the exact values. So that's why I think this is a really good warm-up question to start with. And I hope that you guys actually enjoy this question as well. All right. So now, can I move on to question 2? Do you guys have any questions? If you have any question, you can just type on the live chat and I can see it immediately. Everyone's so quiet. Okay, let's move on to the second question. I hope that everyone's doing well during this lockdown period. So today is the first day of the lockdown, I think. Yep. Can I erase this part as well? Okay. So make sure that you go back to the video again. You can actually rewind and pause, and then you can write down all the notes again. Okay. Let's have the second question. The second question, oh, I need to bring my question up as well. So the second question is, if z to the power 5 is equal to 1, show that alpha plus alpha squared plus alpha cubed plus alpha to the power 4 is equal to -1. Okay. Okay. Now let's have a look. Z to the power 5 is equal to 1. Okay. And then they're saying that alpha is a root, okay, because they use lots of alphas here. So if alpha is a root, that means I can say alpha to the power 5 is equal to 1. Now, the question didn't really say that you need to find the root, but they ask you to find alpha plus alpha squared plus alpha cubed plus alpha to the power 4 plus 1 equals 0. Now, this actually gives me the hint. I might need to factorize something. So I'm going to move this 1 to the left-hand side. So that will give me alpha to the power 5 take away 1 is equal to 0. Okay. How am I going to factorize this one? We have a hint from here. If alpha to the power 5 is equal to 1, we know that immediately one of the solution is 1. So from here, I know that one of the solution is 1. Okay, so this tells me that alpha take away 1 is a factor. So I can say this multiplied by something can be equal to 0. So, okay, now let's have a look. I can rewrite this, but I'm going to use synthetic divisions because I'm the fan of synthetic division because it saves my space and it's quicker. So what I'm going to do is I'm going to write the coefficients of the original equation here. Everything start from the highest power to the lowest power in order not missing anything out. So the first coefficient is 1, and obviously we don't have the alpha to the power 4, so I put 0, and then alpha to the power 3, 0, alpha to the power 2, 0, and also alpha is 0, and then at the end we have a constant -1. Okay, so we draw a ladder here because we are using the first root solution that we got, which is alpha equal to 1. So I'm putting this 1 on the left-hand side. So start from the first stage. There's no number here, so it's equal to 0. So you add them together, will give you 1. 1 times 1, you write the answer here. Again, you add it. So 1 times 1 is 1. You add it is 1. 1 times 1 is 1. Plus them together is 1. 1 times 1 is 1. Plus them is 1. 1 times 1 is 1 again. And minus 1 and plus 1 is 0. Okay, so let's have a look. If you keep looking at this, This is what alpha to the power of 5 negative 1 divided by x negative 1 is. This is the result. So if alpha to the power of 5 divided by alpha, then we'll get alpha to the power of 4. So this actually tells me alpha to the power of 4. This is coefficient of the alpha to the power of 4. This is coefficient of alpha to the power of 3. And this will be coefficient of alpha to the power of 2. And this is plus alpha, and then the last one is constant. Now from here, what we can see is alpha to the power of 5 take away 1 is equivalent to alpha take away 1, which is the factor that we got here, multiplied by this whole thing, which is alpha to the power of 4 plus alpha to the power of 3, alpha to the power of 2 plus alpha plus 1, is equal to 0. Okay, so if we say that alpha take away 1 is 0, okay, when we solve this, then this whole thing is equivalent to what? This is also equal to 0. And what does the question ask for? The question asks that you need to prove that this part is equal to negative 1. So let's just write it out. So alpha to the power of 4, alpha to the power of 3 plus alpha squared plus alpha plus 1 equals 0. All I need to do is move this positive 1 to the other side, and we got the conclusion here. So this is what is required. So I'm just going to say as required. Okay. Everyone so good so far? Everyone all good? Okay. Now let me go back to the question again. I forgot what's the second part of the question. Okay, so the second part of the question, absolutely, Sam. I think you can use the sum of the roots. That's totally fine. Let's see. So hence find the equation with a real coefficient whose roots are a alpha plus alpha to the power of 4. So I'm going to write down here. So the roots are alpha plus alpha to the power of 4 and what is that? Alpha squared plus alpha cubed. Okay, now here we are going to use Sam's idea. Sum of the roots. Okay, so let's start with sum of the roots first. Okay, so that will give me alpha plus alpha to the power of 4 plus alpha squared plus alpha 3. What does it look like? Does it look like what we got here from the first part, which is the first part they put it in order. This is just not in order, but it has all the elements that is required. So this is equivalent to negative 1. So we know the sum of the product is negative 1. And let's have a look at the product of roots. By the way, this question actually has another different way to do it. So we don't just need to fix to this method. You can do whatever method that works for you. So the product of roots is alpha times plus alpha, and then alpha squared plus alpha cubed. And then let's just expand it nicely. So we got alpha cubed plus alpha to the power of 4 plus alpha to the power of 6 plus alpha to the power of 7. Okay, now I just need to pause here a little bit. That's what I did. Because when I was looking at it, it's not really straightforward. It has alpha cubed, alpha to the power of 4. But suddenly I got alpha to the power of 6 and 7. And I'm just observing the whole working that I have done so far. And then I pay one attention here, which is alpha to the power of 5 is equal to 1. That actually jumped into my eyes. So that's why at that time I decided maybe what I can do is I can take the common factor alpha to the power of 5 out first and see what it looks like. So what I did is alpha to the power of 3, alpha to the power of 4 plus alpha to the power of 5, and that will give me alpha plus alpha squared. And from here, what I know is I can substitute the value of the alpha to the power of 5 that I know here, which is equal to 1. So this is equivalent to 1. What that means is at the end, I am getting alpha cubed plus alpha to the power of 4 plus alpha squared. And if you look at this, what does it look like? Does it look like, again, the first part, what they are asked for? And then we already proved it. So which means this is equal to -1. So now what we have is the sum of the roots is -1. We also know the product of the roots also -1. So now we definitely can find the equation of this whole thing. So there'll be z squared. Remember, I'm just going to write it first. It's always z squared take away sum of the roots. Z and then plus product of the roots. Yep, equal to 0. So which means this will be z squared take away -1z and plus the product, which is -1 equal to 0. And that will be z squared plus z take away 1 equal to 0. Okay, now we got the answer. We found the equation whose roots are alpha plus alpha to the power 4 and alpha squared plus alpha cubed. It's okay? You all right? Okay, sorry. Okay, so can you please quickly have a look at question 3 now? And I just go to attend my son and I'll be back soon. Okay, I'm back. So does everyone understand why do the product of the roots is -1? Okay, Josh, what you need to do is you need to pay attention here, especially this part. You can see the wavy line here. What I have done is I take the common factor of alpha to the power 5 out. Okay, so I took the alpha to the power 5 out, so that will give me alpha plus alpha squared. So you just check if you multiply here. But from the beginning, we know that alpha to the power 5 is equal to 1. So I substitute back into here. So therefore, at the end, I'll get exact same expression, which is alpha plus alpha squared plus alpha cubed plus alpha to the power 4, which is from the top 1. Okay. All right. Somebody already noticed that. You can see the link between question 2 and question 4. Good job. Now, there are actually another way of doing it, which is you can actually get the roots of all of this, all 5 roots. And using the 5 roots, you can actually see the relationship between alpha and alpha to the power 4 and alpha squared and alpha to the power 3. You probably notice that it's perfectly, they're conjugates. So when you're actually putting them together, it will actually give you the same results. So what I'm going to do is I'm going to scan that part of working and I'm going to upload it to the Google Classroom so you can have a look. That's a really nice approach as well. So I'm just quickly going to erase this part and we are going to move on to question 3. All right, question 3 does require the knowledge of the sequence and series. So I think for the first part, which is a linear sequence, you guys should be fine with that. And I'm not sure how many of you actually learned the geometric sequence. And for the geometric sequence, the formula is actually will be given to you on the formula sheet. So it's not something that you have to memorize it, but you just need to learn how to actually recognize the pattern of the geometric sequence. Okay, so let's start. So question 3. Okay, let me pull the questions out again. So it says z to the power of k is equal to w, and then k belongs to, k is a natural number. So that's what that signal, that symbol actually means. Show that the sum of the k roots, so basically sum of all roots equal to 0. So that's what they asked us to find, and it says k is any real number, okay? Now, because it says k is any real number, so for this case, I'm just going to assume that w is a positive real number. Okay, so now what I'm going to do is I'm just going to look for the roots because they ask for the sum of all roots. So we're going to find the roots, use the unity of the roots. So firstly, I have z to the power of k is equal to w. And then now, if this is real number, let's just say simply the w is here. Okay. So therefore, this will be w cis 0. Okay, z to the power of k is w cis 0. Use the De Moivre's theorem next step. Let's say if let z equal to r cis theta. So what that means here is this is z to the power of k. So it will be r to the power of k and cis the k amount of theta, which is equal to w cis 0. So here we can get r to the power of k is equal to w. So therefore r is equal to k root of w. Thank you. Thank you. I love you. And then, good job. And then from here, I can say that k theta is equal to 0. So theta is equal to 0. So from here, we can get the first solution, which is z1. I'm going to write it here. So z1 is equal to k root of w cis 0. Now let's just go back to the original question. It's z to the power of k. So that means how many solutions do we have? We have k amount of solutions. And that means every, what is the equal gap? The equal gap between the solutions will be 2 pi over k. So the gap between solutions will be 2 pi over k. So now what I just need to do is the second solution will be just keep rotating. So you're just going to add this gap to the previous argument. So there will be 2 pi over k, and you'll be going. So this z to z third solution will be adding another 2 pi over k. So it's 4 pi over k. You keep going. So next one will be 6 pi over k, and keep going. And you probably ask, do I have to keep going for so long? And all the way until we have z to the power z. The case one is okay. Now let's pay attention. What should go into this bracket here? I just want to practice our linear sequence here. If you just all we need to focus on is the angle. So the angle is constantly increased by 2 pi on k. Okay, so this is a difference. So we actually learned the difference. So let's have a look. In order to get the first one, in order to get the first pattern here, so the difference multiplied by the pattern number 1, and that will give me 2 pi over k. It's not 0. So I need to take away another 2 pi over k to get to 0. So that's the first pattern. Let's just double check whether it works for the second one as well. So again, the difference 2 pi over k times by the second pattern number. So that will give us 4 pi over k. So in order to get 2 pi over k, I need to take away 2 pi on k. So this actually tells me the rule for this linear sequence is the difference 2 pi on k times by the, for this case is k. Okay, so k's pattern, take away 2 pi on k. Okay, so if I just tidy up a little bit, there will be 2 pi bracket k minus 1. So I just combine them together as one fraction. So, and then I can see the common factor is 2 pi. So I take the 2 pi out, so I got k minus 1 here. So I can write 2 pi k minus 1 over k. Right, and can you see the writing on the board clearly, especially on the right-hand side? Okay. Now, let's keep looking at what can we do. So now we are trying to find the sum of all roots together. So if we want to find the sum of all roots, we just need to look at what kind of pattern exists in this sum of the roots. Okay, kids, can you please Okay, so let's have a look. Z1 is this, Z2 is this, Z3 is this. Dominique, can you please go to the other living room? Thank you. Thank you. Okay, so I know that I can't really see whether there's any linear sequence or not, but let's check whether this is a geometric sequence. Now, before I dive into it, so I just give you one example of the geometric sequence. So I go 1, 2, 4, 8. This is called geometric sequence. And if you can notice that, it's always multiply by 2 times by 2 times by 2, you give the next number. So we have a common ratio of 2. So if we can see the common ratio, that means this is the geometric sequence. Okay, so we are going to check. So let's have a look at here. If Z2 divided by Z1, what do we get? So according to the math theorem here, what you do is the modulus divided by modulus, so which will give us 1. So I'm just going to write everything down. And then angle, what we do is the one angle take away another angle. So that will give us 2 pi on k take away 0. Now, so this will be this 2 pi on k. Now let's just check other sets. So make sure that we actually have the common ratios here. So we have Z3 over Z2. So again, the modulus is always the same. When we divide, it's 1. And then we're going to take away the angle. So it's 4 pi on k. Take away 2 pi on k. So that will give us this 2 pi on k. So now I can confirm that this is a geometric sequence. So if you look at the formula sheet has the sum of all for the geometric sequence. So the sum is equivalent to A times 1 take away R to the K, and then divided by 1 minus R. So that is a formula that you can use to find the sum. Now what this A represents is actually the A is first term in the sequence, and R represents common ratio. Okay, so I'm going to just sub everything into this formula here. So all I need is, in order to find the sum, is the first term and the common ratio. So we have first term, which is Z1, and I have the common ratio, which is this 2 pi on k. So now I'm gonna erase most of the stuff on the right hand side. Okay. All I need is this one. This is A, and I have common ratio R here. Now let's do this. So the sum is equivalent to Z1, Z1, and 1 minus, and the common ratio is cis. So cis 2 pi over kth power, and divided by 1 take away R. So which is cis 2 pi over k. Now, let's just keep working on this. So I'm going to work on this first because that has a power of k. So cis 2 pi, this whole thing to the power of k, again, use the math theorem, will be equal to, the modulus is 1, 1 to the power of k is still 1, and the angle will be k amount of 2 pi on k. And we can see here, we can cancel k and k together, so that will give me cis 2 pi. So now I can actually figure out the actual value of cis 2 pi. So that is same as cosine 2 pi plus I sine 2 pi. Now think about 2 pi is equal to what? 2 pi is 1 revolution. It's back to the starting point, which is 0 degrees. And cosine 0 degrees is same as 1. I hope that you got the picture of the unit circle in front of you. So if you got the unit circle here, we know that the radius is 1, so there's 1, 0. And then we actually explore the coordinate of this. This is same as cosine, and the y value is actually the sine. So the cosine 0 is 1, and the I sine 0 is 0. So therefore, it's 1. Now, I'm going to substitute this into the equation that we got for the sum. And we really actually notice that I don't need to keep going too far, and I can find the answer soon. Because S is equal to K root of 6, 0, 1 take away. We already figured out this whole thing is equal to 1. So it's 1 take away 1. What is 1 take away 1? Is 0. So on the top, 0 times whatever is equal to 0. So the whole thing is equal to 0. So we just proved that the sum of all roots equal to 0. Okay. All right. Okay. Anyone, just a quick question. Is it actually on the formula sheet or is it not on the formula sheet? I actually can't remember. I thought it's actually on the formula sheet for the sequence thing. Let's have a look. All right, Andrew, did you say that we need to state k doesn't equal to 1, right? Because that will give the denominator. Yes, that's right. Absolutely. So there is a condition that we have to say k cannot be equal to 1. Well done. Okay, so if it's not on the formula sheet, you guys need to actually memorize this formula for the sum of the geometric sequence. Okay, just one tiny thing to remember, because it's not them. You don't have to memorize all the formulas anyway. Yep, good job. Okay, so now let's have a look at question 4. Everyone's feeling okay? Not feeling like overwhelmed? We still got time, so yes, good. Okay, so question 4, if you look at it, it looks quite similar to question 2. Now again, maybe some of you might have different approach from me. Okay, so let's have a look at question 2. So again, it says z to the power 5 is equal to 1. And then you're going to express z to the power 4 cube and as the, okay, this question is slightly different. It says you have to express that expression as a product of quadratic functions. Okay, so that means one quadratic multiplied by another quadratic. But if quadratic times by another quadratic, we know that the power is going to be z to the power 4. Yeah. So let's just start doing this. So from the previous question 2, we can make the conclusion that z to the power 5 take away 1 is equal to 0. And we use the synthetic division and gave us the factorized format. So there will be z take away 1, and we have z to the power 4 plus z to the power 3 plus z squared plus z plus 1 equal to 0. This is what we got from question 1. Oh, sorry, question 2. Now, we need to actually show this part as the product of the quadratic. So we need to find the roots of this. But another way to write this is I can use all the roots. So this is z to the power 5. So it has 5 roots. So I can say that z take away z1 multiplied by z take away z2 multiplied by z take away z3 multiplied by z take away z4 and multiply z take away z5 equal to 0. So these two equations are equivalent to each other, but actually showing the same thing. Now, what I can do here is I can just assume the first solution, z1 is equal to 1. So what that tells me is this whole thing, the second bracket here, is actually same as everything that is underneath, if you can see, which is z minus z2, z minus Z3, Z minus Z4, Z minus Z5. Now let's quickly use the unity of the circle, or symmetry of the circle. Yes, we do have a circle. Thank you. Okay, so let's quickly find what Z1, Z2, Z3, Z5, Z5 is. So we have the first one, we know that is 1, so which is equivalent to cis 0. Yep. And then it has 5 different solutions. And then each gap between solution will be 2 pi on 5. And then this one will help me to find the second solution, which is cis 0 plus 2 pi on 5. And the third solution is cis plus another 2 pi on 5, so 4 pi on 5. Now, if I put another 2 pi on 5, that will hit the trump wall. So I just don't want to do it. I want to go another way around. So the fourth solution is I'm starting from this point, going clockwise. So that will give me cis negative 2 pi on 5, which is conjugate of the second solution here. And then the last solution will be keep going the other way around. So that will give me negative 4 pi on 5. Okay. Now, using the trump wall, I can easily get another 2. And then notice that Z2 and Z3 are conjugates, and Z3 and Z5 are also conjugates. Now I'm going to substitute all of this into here. Oh my goodness, now I feel like I need a really large whiteboard. Okay, let's just do it. So I have Z minus Z2, cis 2 pi on 5, Z minus cis 4 pi on 5, and Z minus cis negative 2 pi on 5, and multiply by Z take away cis negative 4 pi on 5. Now what I want to focus is looking for something quite similar to each other. So I have Z minus cis 2 pi on 5, and I also can see Z minus cis negative 2 pi on 5. And another one is, just going to use different color, is this one and this one here. So now what I'm going to do is I put these, multiply these two things, the red color ones, together. So that will give me Z squared minus Z bracket, so cis 2 pi on 5 plus cis negative 2 pi on 5, and then multiply these two things here. There'll be positive cis times by 2 pi on 5 multiplied by cis negative 2 pi on 5. Now, before I move on to the next, the purple lines here, let's just have a look at this. So what you got is two conjugates are adding together. So this, if you look at the picture, so this probably, okay, we don't need to use a picture, so just want to save the space. So this is actually same as cosine 2 pi on 5 plus I sine 2 pi on 5 and plus cosine negative 2 pi on 5 plus I sine negative 2 pi on 5. Okay, I need to stop using the red color. Not sure whether you can see it nicely or not. Okay, so what is the relationship? What is a couple of approaches? You can use ASTC and draw it on the diagrams to see it, the relationship. This is what I want to ask. For some of you already learned the trig functions and graphs. What is so special of the cosine function? Is it even function or is it odd function? We know that the cosine looks like this. So it's an even function. What that means is when we have a negative angles, that is actually equivalent to the cosine 2 pi on 5. And what about sine? Sine is a, so if you look at the picture, that's what it looks like. It's symmetrical to the origin. So that is an even, there's an odd function. So when we have a negative values, that is actually same as negative sine of the positive angle. So I can use the even some odd function properties to help me to simplify this whole thing. So at the end, from here, I can conclude I have the two of the same cosine. So there'll be 2 cosine 2 pi over 5. And if you pay attention, so what you have is negative sign and positive sign. So they will cancel each other, become 0. So when you add the conjugate pairs, okay, so if you have z plus z bar, so that will be actually same as 2 of the real parts of the conjugate. Sorry, not conjugate, the complex number. So this is same as the 2 of the real part of the complex number. So I hope that you can actually remember this, because this will be actually saving a lot of time when you're doing the scholarship questions. Okay, so now I know that. Okay, I'm just going to write on the left-hand side. So this will actually speed up the whole thing, because the second one, the purple lines, when you actually expand it, it will give you a similar format. You will have the conjugate pairs adding together. You will have the conjugate pairs multiplying together. Now what I want you to think about is what's going to happen if I multiply conjugate pairs? What's the answer of that? Okay, now let's just quickly have a look at here. I have 6 2 pi on 5 times 5, 6 negative 2 pi on 5. We can use the Molar theorem that we learned. When we multiply two polar forms, all we need to do is add the angles together. So what we got here is 2 pi on 5 plus negative 2 pi on 5. What do we get? Is 6, 0. So 6, 0 is same as cosine 0 plus I sine 0. And cosine 0 is equal to, so I'm going to write it here, 6, 0 is equal to cosine 0 plus I sine 0. So therefore, it is 1 plus 0. So it's equal to 1. Now we're going to use this. Just make sure that we write everything down. So from here, what we got is, I got z squared, take away z, we have 2 cosine 2 pi over 5 plus, now we have 1 multiplied by z squared, take away z. Now I'm just quickly write this down here. We got 6 4 pi on 5 plus 6 negative 4 pi on 5, and then plus 6 4 pi on 5 times by 6 negative 4 pi on 5. Okay, again, just quickly use the properties that we actually discovered here. When you add the conjugate pairs together, the real part for this is cosine, so that will give us straight away 2 cosine 4 pi on 5. And when you multiply the conjugates together, this one, again, you can use the Molar theorem here. So angles add up together, give us 0. So therefore, it gives us the cosine 0, so it's equal to 1. So now I can tidy up a little bit. So that will be z squared minus z 2 cosine 2 pi on 5 plus 1 multiplied by z, take away z 2 cos 4 pi on 5 plus 1. Okay, now we just showed that this is actually a product of two quadratics. So we got two quadratics. We already showed that's a product. So now the next step is to find out the value of cosine 2 pi on 5 times the cosine 4 pi on 5. So all we need to do is just expand a little bit and then see whether we can actually find cosine 2 pi on 5 times by cosine 4 pi on 5. So let's do this. So I got the x to the power 4, take away x cubed, and 2 cos 4 pi on 5, and then plus z squared, and then take away z cubed. I have 2 cos 2 pi on 5, and hold on, just make sure that I'm not lost. Am I doing this? Z cubed. Yep. Please check on me, make sure that I'm not wrong. And what am I doing next? So I just did this one here. So I'm gonna do plus z squared. Okay, maybe I'm just gonna write it underneath. So I have z squared 2 cos 4 pi on 5 and multiply by 2 cos 2 pi on 5. Yep. And I can keep going next, which is minus z 2 cos 2 pi on 5. And then I finish this. Now I'm just have 1 multiplied by everything. So that'll be z squared take away z 2 cos 4 pi on 5 plus 1. Okay, now this is a really long one. But now, when I was looking at this, I'm always trying to observe first before I keep going to the next. So I can see that our aim is to find the cosine 2 pi on 5 multiplied by cosine 4 pi on 5. The only thing that has a multiplication of these two things is this term here. And this is the coefficient of the z squared. So what that means is all I need to focus on is the z squared coefficient. Because I know this whole expression is actually equal to z to the power 4 plus z to the power 3 plus z squared plus z and plus 1. Okay, so all I need to do is matching the coefficients. So coefficient of z squared is 1 from here. And now I'm just going to collect all the coefficients of the z squared from this long expression here. So that will give me, you have one of them, you have another one here. So this is 2. So I'm going to write on the right hand side. So on the right hand side, okay, I'm going to write, so there'll be 2z squared plus 2 cos 4 pi on 5 multiplied by 2 cos 2 pi on 5. So this is the coefficient of the z squared, which is equal to 1. Now it's actually getting really nice. That will actually help us to find the final answer. So I have 2, 2, 2. I can see I can take the common factor out. So that will give me 1 plus cosine 4 pi on 5 times by cos 2 pi on 5. Okay. The whole thing is equal to 1, which means this whole thing is equal to half. Okay, now all I need to do is bring this one to the other side. That will give us negative half. Oh, sorry, I made a mistake here. Just realized it. When I take this one out, I still have a 2 here. Okay, so there'll be 2 of this equal to negative half. So the final answer should be equal to negative quarter. Yay, we got it. We got the answer. Sorry, I missed out a 2 here because I just simply look at this and then try to get everything out. Thank you so much. Okay, do you feel like this is all right? And I think this video is automatically saved, so you can actually watch it again just by going back, and you can pause and just take the notes and just try to figure out how I did it. And if you have any more questions, just let me know. So the next scholarship session will be not during the holiday time, but I'm actually going to upload the session 6 questions and probably session 7 questions as well, because both are complex number questions. So I try to finish complex number by week 2 of term 2, and then we can actually move on to trigonometry. So I will give you 2 sessions of the questions. We have slightly more sessions on complex number compared to last year, and it's just purely because I'm actually chucking a bit of more questions into the scholarship session part. Okay, so just check your Google Classroom and make sure you do those questions during the holiday time. And then the week 1 of the term 1 will be back for the live lesson if the lockdown is still, oh yeah, it's gonna be here. Yeah, so it's gonna be live lesson. Okay, thank you, gentlemen. Have a lovely day.